Welcome everyone. In this video, we are going to solidify our understanding of Big O notation, that's complexity, by breaking down the top 10 interview questions and answers. So let's dive right in. Our first question is, what is Big O notation and why do we need it? What's the difference between time and space complexity? So imagine we have two automobiles, that means cars. So car 1 consumes 1 liters of fuel 10 kilometers and car 2 consumes 2 liters, that's constant 10 kilometers, and based on this consumption, 20 liters it consumes for 100 kilometers, 10 liters it consumes the first car 100 kilometers. What is the difference between them? Basically, both cars travel the exact same distance. Our input size is identical because, however, car 2 consumes, as we can see, resources at a little bit higher rate. That means 2x higher. That car 1, if we calculate and make its function, let's say Tn equals to 0.1 multiplied by n, because if we divide it 1 by 10, it becomes 0.1. And based on this function, this is the first cars, let's say we can say the function, when n equals to 10, then it becomes 1 liters. When n becomes 100, then its consumption becomes 10 liters, and etc. And second cars function also becomes multiplication by n, but 0.2. n equals to 10, then becomes 2 liters. When n becomes 100, then its consumption becomes 20 liters, and etc. And if we write down or sketch into its function, we can see this is the n, let's say this is the Tn function. When input becomes 10 and 100, it becomes in vertically 1 liters and 10 liters. We connect dots and we can sketch the linear growth the same. And second cars also the sketch linear path also will be same because the growths are the same. Main difference is car 2 has a larger constant factor, meaning its resource consumption is twice as high. In the car analogy, resource was fuel. And in algorithms, the two core resources we care about that means we have as we talked before, time complexity. How does the computational work grow as the input size increases? And while space complexity shows that how does the memory required by the algorithm grow as the input size increases. The main thing is computational work, not actually like the seconds or minutes, and of course memory, how changes as the gross input size increases. So all in all, based on these conceptions and this tradition, we can say both of cases complexity becomes O of n. Why it's not 0.1 like these constant factors, we drop it. The nice question. So in that, based on the upper bounds that Big O notations rule is we need to drop constants firstly and lower order terms in Big O notation. We can see the mathematical proof. Let's look at the one function with another little bit higher function, which is 3 multiplied by n plus 10, let's say, where n is the input size, as we know. So 3 is constant factor, and 10 is constant term, we can say, constant term. As n grows larger, that constant 10 stays fixed, as we know. When and while n scales upwards, let's say for example n equals to 10, we can calculate Tn equals to 3 multiplied by 10, 30 plus 10, it becomes 40. The last result was, let's say, constant term 10 and our result 40. What does it mean? The 10 is expected that result, the final result. But when our input size becomes, let's say, 1 million, then Tn becomes 3 multiplied by 1 million, 3 million, plus 10, 3 million, just 10. What does it mean? So, in that case, as input size increases, adding 10 has almost negligible effect. But the last case, when input size is a little bit not higher, it was eligible. That means eligible affected. Therefore, for large inputs, the growth of 3n plus 10 is completely dominated by 3n, we can see in here, which is a constant factor. We ignore as well, of course, 0.2 as a last result example, and 3 as well, or it becomes, might be, or would be 10 or 100, 10, 100 or 1 million. Because of constant multipliers change the scale linearly, but they don't change the growth class. That's why. Thus, we are left with On. In our function head, let's say, we can drop them, and final result also becomes O of n. If our function had, let's say, n squared term, like n quadratic term, 3 multiplied 10 over 2, n over 2 plus 3n plus 10, it will become, the results also would be 0.n squared. This is a constant factor, and this is a lower term as well, and based on that case, this is the higher grade, and we just drop constant factor in here. So this process, this mathematical process, we can call in a programming like the world's asymptotic notation or asymptotic upper bound. So big O is basically represents the asymptotic upper bound, and upper bound means finding a ceilings. Like we need to constant C and let's say constant N0, such as all of the, we need to find, let's say, constant C and a constant N0, such as that for all n greater or equals than N0, our actual function is always less than or equal to S multiplied by n. If it has, let's say, S, we're equaling to the 4 and 3n plus n, this value, this function, or this, let's say, the equality is have to less or equals than 4n. What does it mean? If you finish that value, if you finish that process, n also becomes greater than or equals than 10. That means that as long as in at least 10, 4n acts as an upper bound for 3n plus 10. If we pick n equals to 1, then put it in here, 3 plus 10, 13. It is actually less than 4 multiplied by 1, which is 4. It's not. Because this behavior, when n is sufficiently large, is what? That is why we can call asymptotic behavior. We will see this behavior's real analogy in the next question, yeah, of course, because it's related on the next question. That means, in shortly, this is the much more exact unique rule for that case. This is also asymptotic behavior. Okay, these are our second and third questions, which are what are the best case, average case, worst case, and are they same as big O, theta, or omega? So, main answer is no. Case and notations are completely separate concepts. Case and notation. So, notation are let's firstly describe about the case. So best, average, and worst case describes the condition of the rule. Okay, let's firstly describe about the case. To use and continue our last example, which is a car analogy, the best, average, or worst cases describes the condition of the road. We can see in here how congested it is, or how smooth it is, or let's say the bumpy the path it is. how much, like, let's say kilometers, or how much, like, the length of that full, based on the full distance of the road, let's say. And the same car and the same road as well for big O, theta, or omega. That types of the notation or bounds are the indicators that measure car speed, let's say car's characterizations, how efficiently it saves distance, like based on his fuels or motors, let's say. We can describe its speed as like time, or distance its space complexity, like these examples. We can see it as a real analogy. So, and then we can see the low-level analysis of the cases. We can continue. So, a case refers to the state of the input passes into the algorithm. Imagine we have like the boxes, and one of them contains jackpot tickets. Only one. We don't know which one. Let's say we have 10 boxes, 10 or packages. One of these inside, the ticket. And that ticket, we don't know which box it has. In the best case, if we are lucky, if we find the ticket in our very first attempt, regardless of whether they are million boxes, it doesn't matter. That is a best case scenario, like T, best, n is equals to 1. That means this is a best case, or of 1, we can say. So in the worst case, if the ticket is in the very last box, that means we have to check every single box. If there is 100 boxes, we need to check like 10 operations or iterations or attempts. If there is a 1 million box, 1 million attempts, and etc. This is the worst case, which is O of n, we can say. And average case, assuming the tickets is equally likely to be any position, like randomly, the average operations required would be roughly, let's say, that n plus 1 over 2 we can consider. These are the types of the cases we can say, and I think it's understandable. So we can say we can see notation as well. Oops. So there are types of the notations as well, which are big O, big theta, and big omega, we can say. There are different notations, which are big O, as we say, the second name is upper bound. That notation answers that question: what is the maximum growth rate that bounds this function from above? Like for our previous function, we can say 3n plus 10 less or equals to 4n. So means its t worst case is O of n. As a real example and analogy, we can say the n rooms to clean them. Let's describe the upper bound based on that function. We have n rooms that we have to clean them. Almost the same positions, almost the same case, almost the same situation. Each room takes, we can see based on this value, each room takes 3 minutes to clean. And plus first attempt, we need plus 10 minutes at the start. I mean at the beginning to prepare our let's say equipment, some things for the cleaning stuffs. And to guarantee, we can say, maximum safe limit for cleaning these rooms, each rooms I mean, we can say that cleaning each room will take no more than 4 minutes. Standard 3 minutes plus something per room, we can say. This is a simpler definition of big O's upper bound. Got it? Yes. And big omega we have, which is lower bound. Let's continue with describe this with this analogy. Firstly, it answers the question: what is the minimum growth? Minimum growth of this function from below. Yeah. We can consider 3n plus 10 less than 3n, let's say. We are like crossing it, lining it, the minimum growth below. So it means the algorithm must do at least 3n works, at least. It cannot drop below that, meaning that for any n, No matter how many rooms there are, each room takes at least 3 minutes to clean, and it can't possible to take less time than that, like the pit stops 2 minutes, 1 minute, like they say. Based on this tradition, we can say this is a main analogy, this is a main concept of the lower bounds. And the last one, big theta, which is tight bound. Yeah, so it bounds the function from both above and below, above and above, using the same gross class, like 3n plus 10 we had, and the maximum upper bound we had the less than the 4n, and we can say 3n as well. That means t worst of n is also becomes n, like the tight bound. Continuing the same analogy, it refines the guarantee by setting a strict limit, like this is a strict full limit from above and below. Like cleaning a room will not exceed 4 minutes and will not take less than 3 minutes as well, falling precisely between 3 and 4 minutes. Yeah, this is our answer. So the next question, 4. So how do we read time and space complexity from code structures and trade off them? That means any kind of the code structures we have, how can we analyze the time and space complexity and how to trade them off? So to analyze an algorithm's time and space complexity, we can follow the main 4 steps, we can see 4 methodology or any other words. So which are, firstly, we need to identify input size. We have to clarify input size as its determinations or its range, like determine what n represents, like for instance it is of a length of array or it's length of like the matrix, how it can be changed, how is it like the static or dynamic, like these things we have to ask from the interviewer, let's say, because this is a main clarification, because this is input, this is the input process, that's why. So, and secondly, we can see the time and space complex based on the complexity. We can calculate the time complexity. So, direct assignments we have, like what kind of the examples we have based on the time complexity calculation. Direct assignments, when we have direct assignments like the simple arithmetics, like we have nums, and we need to find firstly the beginning start element of the nums. We can easily take this, it takes the O of 1 time complexity. And when we have the second case, or this is also we can continue at nums minus 1, which is the last element when we can take, this is also the same result will become. And when we have the second, as a second example, like 1 time, like the single loop from, let's say, 1 or 0 to n, we can take O of n. The worst case, the worst time complexity case. And when nested loops, it also depends on the loop's range, like the nested loops when we face it, and first loop becomes n, the second loop also becomes n, then it becomes n of 2, which is quadratic time, also its time complexity becomes. And the third one, we can see the space complexity calculation. When we are calculating space complexity, we need to look at the input size, of course, like space takes given arguments, and like the input space we have the main 2 types of the spaces, and then auxiliary space, which is extra space. We will see the more deeply than the next questions, like it becomes when our input is the static, which is we are not creating any extras like the spaces. Let's base it on the example of the arrays. We are given the nums array. That means can we calculate the next algorithms without changing this let's say the array? That means can we easily work with only that array or not? If yes, we can use only one input size, not any extra space. That means this is also depends on the situation as well. So the next example is based on the space complexity. When there are simple variables like the I, finding the, or sum, or counts, we can say it's simple, like the space complexity becomes O of 1, the worst case. We can analyze with these methods inside the space complexity. And the last methodology is we can find bottleneck, if there is, like bottleneck we can call, and compare trade-off. Means that identify where the algorithm performs excessive operations or consumes too much memory, extra memory we can say. And then based on the trade-off, in terms of the trade-off, we have to decide that at the end of the day, let's say, we need to decide whether we can sacrifice space or time, or etc. Opposite, vice versa, whereas either time or either space, like this. This is also called space-time trade-off. Another trick question we have, like, why do we need trade-off both the time and space complexity in any, let's say, our solutions? Why do we need this trade-off, like based on in terms of the space and the time? Nice question. The answer is because when we provide solution, the output simply matches expected result. It doesn't mean that we completely solve it. Like our output when becomes exactly expected result, that doesn't mean we completely solved that problem. Not only solution, but also we have to think about maximizing or gains both time wins and space also maximum as much as we can win, like the win-win, both parts. We have to think about that. That means our solution must manage space in a balanced way and deliver the output right when needed, even when heavy, like the loads arrive in the future, let's say. So as a consequence, since nothing in the real life is ideal, in some cases we have to compromise slightly on one and put on another priority. Like we have to filter them as a priority ways. That means much like the golden rule of the mechanics, if any object gains in work and it loses in force, and if gains in force, it loses in the work, like this. So we can see the little example by analyzing time and the space trade-off with some exercises from the LeetCode that we saw earlier by using our 4-step methodology. That we are given the parts, you are given an array of integers, nums, and integer target that return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. This is rule. And examples: when inputs are 2, 7, 11, and 15, target is 9, and our output needs to be 0 and 1 element. That's the element. Or indices. Explanation: why? Because num's zero's index, and plus num's first index becomes 9, because 2 plus 7 becomes 9. So what we can do, firstly, we usually analyze with simpler and faster way, which is a brute force. We can see its codes in the below. So we can see in here it's like a screenshot format. This is let's say the first our solution, faster solution, which is we usually call it brute force, as I said. So we have input size already have, which is nums 2, 7, 11, and 15. Yeah, and our target would be 9. So we have input size already. We complete the first our methodology. Second one is time complexity. We need to calculate. This is exactly we have cleared this part. The time complexity, there are a nested loop, as we can see in here. I and j, we can say these are the indices, like the variables of each loops. The first loop runs n times, we can see, based on its last range, and the second loop runs n by 2 times. Why? Because it is because of its range starts from I plus 1 to n, the last range. We can see at each time g indexes run times becomes more shorter by shorter, but however, in the worst case, its last range becomes the worst case it might to n times, because it is operators. That's therefore n, the first outer loop and inner loop also becomes the worst case n. Then it becomes quadratic time, n quadratic. We calculated it, O of n quadratic, and third analysis is space complexity. In that case solution, there is no an extra data structure is opened, like only we used the nums array. We didn't open any kind of the sense seed or something, or any extra elements or data structures. So, and there are only g and I index variables. So based on this process, we can say its complexity, space complexity is O of 1 or O of n, the worst case we can say. So last one, conclusion. Bottleneck, and then conclusion of the time and space trade-offs. So brute force solution shows the time is we can say that the O of n square, n quadratic, and space is O of n. If is there any bottleneck point, so it uses an inner loop every time to find second element. That is why it also becomes the O of n quadratic time. That also becomes one bottleneck when input size comes the bigger sizes as well. So all in all, time is O of n quadratic, space is O of n. So, and based on the mechanics golden rule, it wins on the force, like spaces, we can say, but actually loses or too much consumes its energy on time complexity. This is our main trade-off conclusion based on the first solution, which is brute force. So now second approach, which is HashMap solution. What we did, firstly, we have input size the same. The length of the nums array it's given on the above. So the next case is we have to find the time complexity, which is in that solution simple loop runs. We can see in here just for I nums enumerate based on the nums array. That simple loop runs of n times because based on the range of the nums, we can say, and time as usual. And searching on array elements through the hash map, we can see in here because we created another the map data structure, and which is diff in the scene as well. We have one condition, which is if condition takes of 1 times. It goes directly to the diff and it compares with these two as a 2 variable. And average time is also based on that all of the elements. We can see that the last one is, which is the bigger one, we can took and we drop of the constant factor in the lower bounds, and we can see O of n is the worst case of the time complexity. And the next our methodology is space complexity. In terms of the space complexity analyzing, we have the nuance, which is all elements are stored in a new hash map named scene. The worst case that hash map saves also the n elements, as that nums stored n elements. That means we have n and we have n as well in that case, but we don't have to multiply them. We have to just add them, sum them, which means O(n) plus O of n then becomes O of 2n, but at the end of the day we have to put only O of n because we dropped as we said, in terms of the upper bound, we have to drop the lowers and constant factors. That's why space complexity also becomes O of n, we can say. So analyze bottleneck point of view practically 0 for this process, we can say, because there is no extra nested loops or repetitive operations, we can say. So all in all, time is O of n, space is also O of n. We speed up the time from O(n) squared to the O(n). This is a main keyword, we can say. and exchange we spent O and space as well. This is our trade, and this is our time and space trade-off. I hope this was good and completely covered the example. Okay, question 5. Why is binary search measured as all log of n? So let's see with a real life analogy as usual. Imagine we have a dictionary, let's say words or sentence dictionary book we have. So with 1024 words or pages, let's say, for easier calculation, and they are sorted alphabetically. If we'll use that case, if you wanted to search some kind of the words in that page related on that page, we have to search that page to page or word by word. Is it called in algorithmic solutions? We usually use the linear search, like step by step. If we use like this scenario, the worst case, we might have to check maybe all 1024 words. That means 1024 attempts. But on the other way, if we take such as index size like the dictionary book, we instinctively, if we use our just the instinct, let's imagine just a real life example, we usually open its let's say middle part to find words that we are looking for. If the words are looking for is, let's say, before or after it, we can just skip that part, we can ignore the other parts, and we continue to the searching for them, like these steps, like this approach. And that case called algorithm we usually call binary search. This is a main analog. So let's continue then with mathematically proof. If we are looking for, let's say the word starts with like S. Firstly, we have to check middle element of the book, like 1024. We can integer division, which is divided by 2, and we can get the main part of that integer, like 5, 12, yeah, yes. And we open that indices or element number and check. Let's say, for example, that page consists M, for instance. So since S comes after M, we can just discard the left half, and look at the right half, we can say. And if we cut remaining half of that 512 by 2, that 256 element left, and so on. So counting the worst case steps down to element 1, we see, like if we continue with these elements, with these steps, 256 divided by again 2, and then it becomes 128. Then if we divide by 2, then 64, then 32, if I'm not wrong, yes, then 16, then 8, then 4, 2, and 1. How many steps we crossed? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Maximum 10 operations to find element among 1024 items instead of 1024 worst case scenario iterations, we would say. So now we can derive the formula from this. If we see the tradition of the computation, search space halves repeatedly. That means the first case, let's say that n by 2, and then n2 by 2, that means n2 over 2, n2 over 3, and etc. until, let's say, n2 over k. This formula we can use. And then we have to continue until the one element remains. And based on this condition, we can just find some formula. That means 2 over k equals to 1. If we want to find the firstly n, that means we can just easily multiply by 10 over k each part, 2 over k, and then mathematically they are dropping themselves, and n equals to 2 over k. And based on this condition, if we find the coefficient like this, it would become logarithmic 2 base of n. This is the main case of binary search complexity. So the tricky question, why is it written as logarithmic n instead of logarithmic 2n? Okay, so this comes from the change of base formula logarithmics, like logarithmic b of n equals to logarithmic c of n divided by logarithmic c of b. we can prove from this formula. That means just a usual simple proof. When we use binary search, we divide it by 2, so we get logarithmic 2 bases of n. Yeah, and if we split into 3 parts, like logarithmic 3 base of n, we usually call it ternary search. Anyways, according to logarithmic rules, also logarithmic 3n, 2n, 4n, etc. differ only by constant factor, because this part is also constant factor, which gets dropped in big O notation and leaving simply by logarithmic n. This is the main proof. So, question 6. Do nested loops always mean O of n quadratic? So, answer is, of course, not always. When we analyzing some kind of these nested loops, we look at the iteration counts and how loop bounds change, not just the presence of nested loops actually. So, and then moreover, nested loops typically fall into 3 main scenarios. So first case, which is when algorithm consists independent loops, like independent loops, then we can say this its complexity of O of n, O of quadratic time, like for I in range, which is n, and for another with the g variable range of n separately, and we can call its function name. So this is separate and this is separate functions. Outer loops runs n times, inner loop also separately runs n times each outer iteration. Then iteration count will be n multiplied by n and a quadratic, we can say. That's why it's you can use quadratic complexity. Second scenario, so multiplicative growth, we can see multiplicative growth with inner loop. So, and we have again for range the same till n, and we have another, let's say the variable which is g is equals to 1, and we are using the while loop. G is to be less than n, and g multiply n equals to 2. That means each time it multiply by 2. So double Smith, that means. So outer loop runs n times as usual, and we can see, but the inner loop, which is a while part, we can see carefully, it doubles each time, like firstly 2, then 1, 2, 4, let's say this 8, like the 2 over index like this. And this is opposite of the binary search, we can say. So inner part taking logarithmic time, and then full nested complexity being also like logarithmic n, and then multiply. We need to multiply because of this nested loop. That's why we don't need to sum them, we have to multiply them. This is the main definition of multiplication growth inner loop. And third scenario is usually called quadratic complexity nested loop, it also looks like, but the name is triangular iteration. Let's say we have this for loop, outer loop, and inner loop is a little bit different, which is I plus 1, then range is n. So first off, if you compare then simple loop, which is like this independent loop, we can say if we put the n each of loop, let's for example 4, then the output will be 4 by 4, 16, If we draw or sketch it with like this, let's say the shape format, it becomes rectangle, rectangle format its shape will be. And based on that case, if we put in here 4, then this case becomes like this operational, another calculation, like for instance when I equals to 0, then the next iteration will be 3. When I equals to 1, the next iteration will be 2. When I is 2, then 1, I is 3, then equals to 0. If we sum them and calculate them, it becomes another version of the calculation, like let's say 1, 2, 3, not 4, only 3 elements, for maximum 4 by 3, 12. It's not becomes like this, that shaped rectangle version. That's why we usually call them triangular iteration. And another mathematical proof let's say based on that cases, we can see n multiplied by n minus 1 by 2 iterations. And if we open that root, n square n quadratic plus n by n over 2, and we drop the low bounds and the constant factor as well, the final result becomes n of quadratic, like this finally it becomes. So now question 7, why do HashMap and HashSet have an average time complexity of O of 1 and worst case of O of n? So answer is basically, firstly, HashSet, we have these two main things, HashMap and HashSet and HashMap. We also use it for that HashSet, and if I'm not wrong, the duplicate contains elements that the exercises, and the HashMap, the two-sum exercise we use it. Firstly, okay, HashSet stores unique elements firstly, like unique values, allowing us to quickly check for duplicates mainly. We also use it, as I said, contains duplicate exercises. So HashMap stores k plus value as a pairs. We also use it in the two-sum exercise as well. So why average case is O of 1? Let's imagine, as a real analogy, we are walking into the pharmacy and asking for some kind of specific medicine, like let's say the paracetamol, or we are searching for that, like the online, the medicine or pharmacy. In a real case, pharmacy doesn't search thousands of the shelves by one, like this. They look up just the index or categorize the system. All of that directly points to the, let's say, correct shelf. The direct access gives O of 1 complexity. That's why the complexity is O of 1. So this is the main reason. And worst case, why is especially O of n? Answer is because of, we usually call it collision, gathering like this. So now suppose we have array which is consist 1, 2, 3 and 1, let's say, and we hash that elements using a modulo operation, modulo, one modulo by, let's say, 5 each of them, and remaining part becomes 1, 2 modulo by 5, remaining part becomes 2, 3 modulo 3, let's say, like this, and we are collecting them in a hash. 1 is consist 1, 2 consists 2, 3 consists 3, etc. And if we wanted to add 1 plus element for that case, let's say 6, then it becomes, let's say, the modulo, and answer becomes 1 remaining part. And then what happens in that case? We already have one element like in our bucket, and notice that both 1 and that 6 result in the same hash location. We say usually, as I said, bucket index is 1. This is called collision. When many case map to the same bucket, so HashMap has to handle collisions. We have to handle them. How? In the worst case, it has to scan all elements in that bucket linearly, and that's why it's taking O of n times, based on our elements count as well. So this is also related on we usually call another name, pigeonhole principle. That means like when n plus 1 elements or items are placed into n buckets, at least one bucket must contain multiple times or multiple items. This is a real proof of the question, and based on that case, we have to, let's say, we have to convert them, append them in the faster approach, and then we have to recite the element and the array then a little bit later. This is also main approach and main process. Next question, what is amortized complexity? Why is append O of 1 and resize O of n? So this is also related on our last topic, like we would say. So before that, let's analyze by array structure. Let's say our array is static, which is fixed, that only has 4 spaces allocated for elements. That means this is like, as in a real analogy, we have, let's say, the chairs and allocated for guests, let's say in our room this is. So having these chairs allocated for guests, but let's imagine 5th guest comes to our home, visit our home in actually, and it shows up there are no chairs left in terms of the chairs count, and we can say that we would wonder that we should do like this, some kind of the bring some fifth chairs, but actually we cannot simply bring fifth chairs because there is a wall where the, let's imagine, fifth chairs would go, and we cannot knock down the entire wall to just one chair. This is a real case. In the same situation, computer has to assign new row for another empty space as well, give new slots, like new elements slots we can say, or bucket for other elements. If it is a dynamic array, there is a still invisible static array underneath, actually, because it depends on the range memory. Resources are limited, because when we append to it here, that case simply writes incoming element into that empty room underneath. Therefore, it usually takes off one time for appending case. Okay, I can append, it's not a problem, which I have some kind of in our elements, between our elements have some one space or two space, that's okay, no problem. But if we have the tons of the elements come and wants to append, what should we do? Or while we are appending them, we need to recite our array as well. That means we have to move all of the guests or that chairs to another bigger living room. This is the main case. This is a main solution as well. So, and during resizing, there is a process of finding new space cam. Let's say that where the new static area allocated that is at least twice 2x large as the old memory. For instance, if we have the 4 elements, the last round, and it becomes at least 8, then migrating it takes n time to n time elements. To ensure that no data lost, actually, it moves them over one by one, beginning of the new array. And after that, the old smallest array is cleared from the memory. So, in the processing point of view, we append, like, let's say, the above array consequently 4 items, and each tool is, let's say, all one time. Now we add, when we added the 5th element, resources run out sometimes, It copied all of the 4 elements, oversize them, taking O(n) time during that interval. If we distribute them across the previous 4 elements and take into account that only one out of 5 times looks such as O of n time, overall during all that n element is accepted at, we usually call it amortized O of 1, amortized thinking we usually call it. To understanding that amortized complexity, we can just give simple example, then I hope you will understand that. So let's say the real world analogy again. Like we have the shop, let's say, and we have one cashier, the worker, its main task is to calculate all of the customers' price and give the receipt, print the receipt, and let's say each of the customer, it usually takes 1 minute standard. And one more thing we have, that cashier needs to upgrade its printers, let's say the paper, each 100 clients, each 100 customers, This is the main rule, let's say. As we talked before, 3n plus 10, that means 3 minutes usual, and one time 10 minutes, each some kind of the result. It also took a time. This is also main calculation part as well, like we usually called maintenance. So let's say the 1 minute it took, and the last 99th client come in here, and the papers are out of the paper in the printer, and then 1 minute plus 10, that means 11 minutes it took. The question is, that mean that cashier did work and work it very slowly? Actually not. It's unfair, because last 99 clients took only 1 minute. To calculate them, to refine them, that case, we usually calculate the total, let's say the 100 minutes plus 10 minutes, 110 minutes. Then we can divide it by all of the clients count. It would become 1.1 minutes. Let's say 1 minute plus 10 seconds, usual. So this process called amortized thinking are algorithms and amortized complexity. All in all, this complexity is usually applied to variable inputs whose quantities are not known in advance. Amortized analysis gives our true long-term cost of each operation when many operations are performed consecutively. So question 9, how do we determine the time and space complexity of a recursive algorithm? So first off, we have to understand about what is recursion. Recursion is, it is a technique where function calling itself on a smaller version of the same problem until that reaches the base case. That means our expected result. So it completely measures how the number of the recursive calls and work per call grow as the input size increase. Again, very real. Let's say the example we are let's say the searching the for file, name it, let's say users.py file. Inside the nested folders structure, let's say we have main project folder, and inside that folder have again system, let's say 24 folder, and inside we have the again backend folder, and inside some users.py, let's say. As a consequence, we have in other files that folders as well, let's say vision 24, and inside some kind of other folders as well. They are not unique folder. In that structure, we don't know the depths of the folders in advance actually. That means we have to only go to the 2 or 3 or 4 projects or the folders, and we can easily find our expected result. This is not like the work like this. That's why we cannot use the only loop formats or nested loops for that problem. If we use, let's say, the for loop for that case, like for file in that folder, and then we want to analyze like for item in folder. If there is no for again item to in item or something else that is continually like this, let's say if it is like this exact structure, you can easily find with some kind of iteration. But actual cases there is no will be like this exact structure, exact like the base case. That's why if we don't know the exact depths, we can use the recursion functions. Like we have a function, let's say scan. Main thing is argument is folder, and we can now use the for loop, but not too much like depth. Folder, it's try to if items in that file, like let's say the equals to file, then we can print. Otherwise, we can just again call that function scan, then item for the argument part. That is the case. Just we can recall the function once, and it can continue to analyze to any depth. This is the main force of the recursion. Yes, it doesn't mean loop is useless. It also can solve with some another ways, but main thing is we need to manage stack ourselves. So, and then moreover, to correctly using the recursion, we have the 2 main cases based on the recursion, which are first case is we call base case, and second one is we usually call recursive case. So base case means condition that stops recursion, when it stops. And recursive case, which part that function recall itself, which part is that function recall itself. This is the main 2 calculations. Let's say if we are using without any of these 2 conditions, let's say we have to have hello, and we are calling again hello, it will not stop. It's unstoppable. It will works. That call we usually call it. There's a popular thing which is stack overflow. This is a function call itself without stopping, and limits error happens. So this is the main case. So to continue to that two cases, when we see the recursion, we need to clarify full condition to find complexity. When the interviewers give us some kind of the task, we have to ask main four questions. Firstly, where is that function's base case? And the second question is how input changes. Input changes in each call. No? And the third question is how many new recursive we have. New recursive calls we have in each call. And the fourth one is how many works to do each call. And last question is how depth is it. This is also related on the recursive case. Depth is recursion. These questions are one of the needable clarifying things, we would say. So last but not least, we have the last question. Where does exponential complexity come from and how do we optimize it? So firstly, exponential complexity usually occurs in problems where are the multiple choices at each step. Like these trees, we would say like this, yes or no, like these multiple options. That means when we need to check all possible combinations. That cases, that problems, we will usually use exponential complexity. So which cases it need for? Let's suppose we have array 1, 2, 3, it consists. The task is that we need to find the biggest element. If we want to find that biggest element, we can just pick one number, one element, and we can compare with others as well. So it is enough to analyze each element to find our biggest at once, because we don't create universe possibilities for each element. But let's say the task is given, find all possible combinations, like 1, or blank version is separate, 1 separate, 2, 3, and then let's say 1 and 2, 1 and 3. If we continue to calculate 1, 2, 3, and 2 of 3 as well, 1, 2, 3, 4, 5, 6, 7, 8 elements, no? This is another thing. So that case appears that should we choose or not that each element, we can need to branch the starts, as I say it, like this version. And based on these combinations counts, we can easily say this is 8 possibilities, you know? Why? Based on this pipeline, we can just prove that its complexity is 2 of n. It depends on the 2's degree, would say. And the next question is how to find its complexity. To find out its space and time, we can space and time, let's say, trade off that or compilation to find out. Firstly, we can analyze the time complexity. There are 2 n subsets, you know, as we say. N set 2 of n, that's the subsets. Constructing or copying each subset takes up to n operations as well. This is a main formula, but it depends on the elements count as well. That's why the total complexity becomes 10 of 2 over, O of n multiplied by 2 over n. This is the main time complexity is worst case, we would say. And space complexity. So recursion doesn't keep the entire tree in memory at once. It explores one path at a time using, we usually call it, backtracking. Like, for instance, for n equals to 3, the maximum depth is that call stack becomes 3. So, and one more thing we need to know is space complexity is, we usually call, to find out full space complexity, auxiliarity space. That means it shows the extra temporary memory for working the algorithm, extend the output, you know. Then let's say we are using the backtrack. For example, backtrack start to work firstly 0, and then it calculates 0. Can I take it or not? If I yes, it can take, for example, 0, or not, we don't take anything. to calculate that cases we need to backtrack in the algorithms. To just instinctively calculating them, it's easy, no problem. But if we have the thousands of the elements, it needs to work like this multiple choice version. That's why we need to backtrack. Then backtrack 1, backtrack 2, backtrack 3, because we have 3 elements. 0 means we have to understand, we have to find out the blank element as well. This is also part of the combination, and for that case the maximum depth is 3. That's why we usually say call stack is O of n, because it depends on the n element size. And the next one is path. We need to find out the auxiliary space. We need these things as well. This is additional concept, we would say. So path, which is a number of the subsets. Number of subsets, we usually say. Its maximum value is also 3, but the main difference is it is which cases we are using, which cases we are in that at the moment. But we need to find out, we need to take into account the number subsets as well. That's why. And for that case, total temporary space, that case we don't have to multiply them, we have to just sum them. On plus again O of n, then it becomes O of n finally in the end of the day. So, and then this is auxiliary space total, but we have the full total space as well, because it also becomes and related on the O of n square as well, and we would say it's total output space and multiply by 2 over n complexity, we would say. Yes.